Hello, I'm Eoin Woods. Welcome to ISAPS. I'm going to be talking today about pragmatic software architecture evaluation. I'm the CTO of a company called Endava. I'm based in London. I've been there about 6 years. I've been doing software quite a while. My hair is starting to go a bit grey. Maybe that's a consequence. I spent over 10 years initially building products for companies like Bull, Sybase and Intertrust. Then I spent about 10 years building large financial systems for capital markets firms. And about 6 years ago, I was lucky enough to move to Endava as my first time as a CTO, and in fact their first time having a CTO, and I've been there since. I've always been a software engineer by training and by practice. I became a software architect 7 or 8 years into my career. I'm now a CTO. And I've always tried to be active in the wider community beyond my own firm. I've written a couple of books. I've written a number of articles over the years. I have some degree of research record as well, though much less than many of the other speakers at this event. What we're going to talk about now is, firstly, we'll introduce what I think architectural evaluation really is. And we'll talk about the different types of architectural evaluation that you could undertake. And I'll be talking about that with a fairly industrial perspective, although I obviously acknowledge all of the research work being done in that field. And I've got 2 case studies, one from somebody else, scenario-based assessment, and one using my method, Tara, on a code base. Obviously at a fairly high level, but hopefully you'll get the idea of what that kind of assessment looks like. And then I'm going to talk a little bit about architectural evaluation in practice. And this is really the shared experience of software architects at Endava who do evaluations for our clients on a weekly basis. And then we'll draw a few conclusions. So, what is architectural evaluation? There's a number of standard definitions. The SARA report's been very influential in this field, and what they say is that it's all about understanding the impact of architectural decisions. How does that affect your architectural requirements? A very valid definition. Bass, Clements and Casman, as you will be aware, one of the classic books in the field, they say it's the process of determining whether the architecture is fit for the purpose it was intended for, and that's important. It's all about context. I define it slightly differently. Everyone's got their own definition, of course, and I say, actually, I look at it as the process. Architectural evaluation is a structured process, it's intentional, to investigate one or more risks or perhaps concerns that specific stakeholders have about the fundamental qualities of a software system. You see, the difference about I'm drawing here is the fact that it's in a very specific context. It's for particular stakeholders and it's about their particular concerns. The reason I define it that way is that in industry, that's normally how an architectural evaluation is framed. So why bother? Why would you evaluate a software architecture? Well, there's a number of ways. Firstly, you may be about to build something and you don't know the risks that you're running. You don't know if it's possible to build them. So let's identify those risks so we can mitigate them. When we're building anything complicated, quality attributes are difficult to assess up front. There is work, of course, in research and simulation, but much of that hasn't reached industry, and much of it, when it is applied to larger problems, is either difficult to apply or actually isn't very reliable. So how might we go about, in a cost-effective way, assessing our quality attributes? That's a good reason to run an evaluation. Could be a kill or cure decision. I've been privileged and sometimes unlucky to be in a couple of these situations. A senior executive realises they've got a problem on their hands. There is a system that, for example, has a lot of production outages or is continually overrunning SLAs or is difficult to maintain or appears to be very expensive to build and operate. And they really want to know, should I just stop this, stop pouring money into it and do something else? Or can I remediate this situation? And that's a very common reason for an architectural evaluation in industry. We may also be looking to validate architectural decisions that might actually be in the context of a kill or cure decision. Have we made some catastrophically poor ones? But it's also sometimes that, in fact very often, we're looking forwards. We are about to make a specific architectural decision and we want to do some evaluation as to whether this decision is likely to be valid or not. We may want to be finding out what architectural practice is like in an organisation or in a community or simply within one system and celebrate the good and promote that. That actually can be a very valid reason for an architectural evaluation. We may need to choose between alternative systems. Imagine two companies coming together in a merger or an acquisition scenario. If they're in the same industry, it is very, very likely they have a large number of systems that do the same thing, one on each side. Which one are you going to keep? Now, there are a wide variety of strategies as to how to go about that, which I'm not going to go into, but you can imagine that you may be in a situation where you may want to make a decision between two systems given a set of requirements. It may also be about acquiring a system. There may be a number of options. Which one should we acquire? We may need to choose between architectural alternatives, and again, we can use evaluation to help us with that. We may be about to acquire a firm. This is something actually Endava does quite a lot for the private equity industry, and some of my colleagues run significant number of architectural evaluations specifically to understand the quality, the utility, and the overall fundamental value of software assets that are being acquired as part of an acquisition. And you may do it just to focus people's attention on architecture. If you decide that you're going to do an architectural evaluation, suddenly architecture becomes much more important in everyone's mind. And that can be valuable in itself. So you can see there's a wide variety of ways to evaluate, a wide variety of reasons we might want to evaluate an architecture. Some of them are relatively political, some of them very, very narrow, some of them very, very broad, some of them very, very technical. So it varies according to who's asking the question and what they're trying to get from the exercise. So what types of architectural evaluation could we perform? So what options do we have if we want to run an architectural evaluation, whatever its purpose? I think there are 5 main varieties of architectural evaluation. There's the scenario-based evaluations, and there are many, many methods for doing this, but they all boil down to identifying architecturally significant scenarios, normally to do with a quality attribute of a system, defining what the stimulus on the system is, how the system should respond, and then analysing whether that's likely. There are simulation-based architectural evaluation methods where we build simulators that simulate the operation of the system in some way, probably using a model-based approach, and then we can apply, for example, workload to it and find out what's likely to occur in the real system. We can have purely analytical-based approaches where we build an entirely mathematical model, a very pure abstraction away from the implementation, and we try and use that, for example, to predict throughput or performance of a system. There are empirical-based methods where we measure the actual system. Let's measure its runtime characteristics, and from those let's draw some conclusions about the system and its qualities. And then the survey-based architectural evaluation, which is more common than you might think, particularly in industrial contexts, often because of the difficulty of getting access to the people and the knowledge to do the other 4 varieties of evaluation. And by survey-based, I mean we put together a structured survey with sets of both closed and open-ended questions. We give that to the key people who know about the system. We ask them to fill it in, then we compare the responses, and we try and draw some conclusions from that. So let's look at each of these in a little bit more detail. Scenario-based evaluation is where we identify a number of scenarios that would stress the system in some way, with respect to something we're specifically interested in. We can identify scenarios by fairly unstructured brainstorming. What is it we wanted to do? We can follow a structured approach. The ATAM quality attribute tree is a very structured approach for doing this. We can use checklists built up from experience. Most consultancies have checklists for common scenarios that they're interested in. We can think about the expected cases. We can think about the things that we can predict. And we can also think about boundary conditions, really extreme cases. All of those scenarios are valuable and investigate different aspects of the system. And what we need to do once we've got the scenario and we've defined the scenario clearly is we need to establish how is the system going to behave during that scenario. That can be pure reasoning, it could be based on testing, it could be based on building simulators and so on. In other words, a scenario-based evaluation can actually use some of the other techniques we mentioned a few moments ago in order to actually investigate the scenarios. The point is that we're trying to find out which decisions affect which qualities. That's really our trade-off points. Wherever we make decisions where the scenarios reveal that we have trade-offs between different qualities. These are often termed sensitivity points. That's what they're called in the ATAM approach. The output of this kind of process is typically the scenarios themselves, failures that we believe are likely to occur, risks that we can see, and trade-offs that we can see that have been made in the architecture. And a well-run scenario-based evaluation with the right people involved, enough time invested, and enough detail in the analysis performed to investigate the scenarios is a very valuable exercise to perform on almost any system. Simulation-based evaluation steps back a little bit and it tries to create a model of the architecture. This is often very useful when you haven't got a system or you've got a very complex system that's rather difficult to work with. And it applies simulation techniques to try and predict behavior. Typically, this is in the performance and scalability area. In principle, it could be used for maintainability or security, but the theory in areas like that for simulation is much less well developed. I'm not aware of tools that will help all that much for other qualities. Most of them are focused on performance and scalability. And the kind of theory that they're using is queuing theory, stochastic algebras, or actual animation of a model. And there are tools like Palladio, AnyLogic, and Magic Draw that will do this for you. Magic Draw is a commercial UML tool, actually, that's got simulation-based evaluation built into it. Palladio, you may well be aware of, as an entire really research ecosystem based around a simulation tool. The idea is, once again, to think about scenarios, but thinking about scenarios that will stress the system and which are interesting to develop a simulation for. The fidelity of the output of simulations, though, is quite difficult to predict. And for me personally, as a practitioner, this is one of their weaknesses. If I don't have the running system to compare it to, if I do have the running system, then arguably maybe I should just use the system and test it rather than using a simulation. It's very hard for me to know how close the outputs of my simulation effort are going to be compared to the real system. There are so many factors involved in even performance of a system, never mind all the other qualities and their interactions. It's very hard to know whether the simulator really is going to give you valid results. Of course, in many situations it can be a useful first step. In some situations where you've got the running system but it's very hard to work with, and you can create a simulation and over time tune the simulation such that it does have good predictability for your system. That can be very valuable. I've used simulation-based evaluation myself, using very informal techniques, writing scripts and doing probably kinds of simulation that would make researchers cringe, but it definitely can be valuable. However, you've always got to bear in mind, how am I going to check that the results of this simulation are actually representative of the real system that I'm thinking of? The other thing about simulation-based evaluation, and I think you'll see this in the literature if you look at it, is that there is often a very major investment in the model building to allow the simulation to be run. And often in industry, that's where this actually runs into the wall. When you look at a non-trivial system, the industrial architects realise it's going to take them weeks and weeks of manpower to build the model to allow the simulation to run without really knowing how useful the simulation is going to be. And that can be a very difficult trade-off to get into, because the return on investment just isn't clear, and to prioritise scarce resources to do it can be difficult to justify. Moving on to analytical evaluation, what I'm talking about here is really mathematical modelling. And by this, we're typically talking about sort of continuous mathematics rather than queuing theory or discrete mathematics. It's quite common again for performance and scalability. I've not seen terribly good ways of applying this to, again, my favourite quality property, security, that I do a lot of work in. Excel is a very common tool in industry for doing this kind of evaluation, and it's often fairly primitive, frankly. Typically what you want to do is investigate the relationship between input conditions and predicted behaviour. So if I have a transaction volume of X, what's my likely throughput going to be? What's the lowest time I'm likely to be able to process that volume in? If I've got a database access time that's increasing over time, for example, because I can't maintain indexes in a timely manner, what's that going to do to my throughput? It's those kind of questions. We're typically looking for relationships between different quantitative metrics. Again, assuring that the model is an accurate abstraction is difficult. And even if the model is in principle correct, calibrating it with the right parameter values can again be difficult. In reality, a limited number of qualities are amenable to this kind of evaluation. It's very cost effective if you can avoid testing. A really good outcome of this is where you can run some isolated tests on a live system perhaps, or a realistic test system, in order to find a set of key tuning parameters. You can create a fairly representative model, a good enough model, that can be parameterized by those parameter values, and you can get reasonably good predictabilities for example, with a transaction volume of X, my batch time is going to be Y. It is possible to do that in some situations. The problem tends to be actually spotting the situations that will cause the model to be invalid, such as I have an unusual transaction mix, which I typically don't have, rather than the actual volume of transactions. Such models can allow you to explore those scenarios, but once again, we've got to be very careful about the fidelity between the predictions of the model and the real behaviours of the system. Empirical evaluation is related to analytical evaluation. The difference is that empirical evaluation is completely based on data you can extract from the system. It's not really about models. It's really about extracting probably mathematical relationships or possibly causal relationships from information that you can extract directly. The good news is that in the last 10 years or so, we've got much better at measuring operational systems. 10 or 15 years ago, this was actually quite difficult because often we weren't building in the measurement mechanisms into the system to allow us to do good empirical evaluation, and they had to be retrofitted, or a lot had to be implied by log scraping and so on. Today there's a whole industrial subfield I'm sure you're aware of called observability, which stresses the need to allow us to understand systems by data that we can collect from them, such as metrics and traces and logs and so on. The principle here really is that if you've got a system, rather than theorizing about it, why don't you measure it? And so this is quite common in many modern software engineering companies today. The internet scalers are definitely people who do this. Most internet-facing systems, empirical evaluation is a big thing for them. They collect a lot of data, they analyze a lot of data, and they visualize a lot of data to give them insights into how their architecture, how their system is behaving in different situations. The approach has to be first to define what you want to understand. There is a tendency to just collect a lot of data, keep it in a huge heap, and then hope it's going to come in handy. Really, that often doesn't come in very handy, because when we need to use it, we find that either the data is unsuitable or we're missing a bit. We need to define what we want to understand, typically a property or a quality of the system. And then we need to design a measurement approach to allow us to reliably measure that. And that's our observability stuff. So we consider both runtime and design time metrics. We look at code. We might look at database structure. We might look at database content in operation. We look at logs. We look at what traces are telling us. We look at what our monitoring tools are telling us. All of this has the advantage of being based on facts. The trade-off is it's actually quite a lot of work typically to take the data and to do evaluation based on it. So one of the problems we often have in industry in practice is that if one of our clients who wants us to do some evaluation has a large data set, it can be difficult to understand the quality of the data set, the semantics of the data set, how the data set has to be processed in order to create insight, as opposed to just having data. And there's also sometimes the problem of what can you measure. There's this inevitable Murphy's Law that whatever you're actually trying to understand, one bit of the puzzle is either difficult to measure or hasn't been measured. And so you're always missing some part of your reasoning, and you have to kind of approximate that part. And as I say, interpreting very large data sets is difficult. However, empirical evaluation is probably the most popular architectural evaluation technique in industry. It is progressing quite quickly, and the parallel interest in data science and data analytics and related visualization is assisting this field a lot. And that, I think, is part of the reason that observability is now of such interest to so many people building industrial systems. So while observability is not itself an evaluation technique, it is an enabler for empirical evaluation. And finally, as I mentioned, the survey-based evaluation. So this is really evaluation based on a set of opinions, and we have to be honest about that. It is no more than aggregating, analysing, and combining a set of opinions, ideally with supporting evidence. We don't always get the supporting evidence, but we always ask for supporting evidence. This is nearly always applicable to an existing system. Running a survey on a future system, as in how will this behave, is probably not useful. That is just speculation. But sometimes you might use surveys to evaluate the suitability of an existing system for for a new situation. The classic here would be an industrial example is when the big vendors implement ERP systems, enterprise resource planning, the large systems like SAP and Oracle. Very frequently, they will have standard questionnaires that they work through with the client, and what they're really doing is, though they may not think of it in these terms, they're really doing an architectural evaluation of the environment into which they're going to try and implement their ERP system, and that's how they know how much hardware or cloud resources they need, how it's got to be configured, what kind of challenges they're going to have. They're aware of limitations in the packages, so they'll know about some of the trade-offs that they'll need to make. They'll be aware of likely problems this client's going to have because they've got a pre-canned survey which they can use with both technical and non-technical stakeholders in the organisation implementing the package. However, the kind of survey-based evaluation I'm really talking about is when typically independent technical consultants are trying to understand a technical environment, maybe more than one system, maybe quite a large number of systems, or maybe one system, and for whatever reason, there isn't time, or there isn't political environment, or there's just no appetite to get further into the actual technical detail of the system. Nobody wants to give the consultants access to the system. The consultants perhaps would take too long to understand the detail of it. It's perhaps difficult to run real live tests on the system for whatever reason that might be. And so we fall back to survey-based evaluation. And actually, I think in my industrial experience, it's quite common that even if we're doing one of the other sorts of evaluation, we'll often do survey-based evaluation too. The reason is that although it's fairly informal, you can make it very structured. You can absolutely focus people's attention on what you need to know. And it's actually very, very efficient, providing you can connect with the right people who have the right knowledge and they're honest and realistic in their answers. Compared to actually testing different parts of a huge system, simply asking an expert what happens when this occurs, or what is your daily transaction volume, at what level does your transaction volume cause you problems, if you can get accurate views on that from an expert, that's a very efficient way to collect a lot of valuable information. The problem is that you don't tend to know the quality of the answers that you get. You don't know if they're lying, or they might be misinformed, or they might be estimating, they're estimating very poorly, or they might just be guessing because they feel they should know an answer and they don't know an answer. So the quality of the answers is often quite difficult to assess. The best we can do is that we compare answers from different experts. Obviously, we ask them to, we either interview them or we ask them to fill in the survey separately. We also do ask for evidence when you say, you know, our transaction volumes are this and our throughput statistics are this. Have you got any actual evidence? Have you got some data for me? Typically the answer is no, or it would be difficult for us to do that, or yes, we've sort of got it, but we don't want to give it to you because it's very sensitive, or some other excuse. But the more evidence we can push for, obviously, the more confidence we have in the answers. The answers also can be quite subjective and difficult to interpret. But as I say, this is quite a common approach in industry because it's relatively easy to do. It's relatively non-intrusive, and that can actually be quite important in many situations. It's pretty efficient, and you can, with the right questionnaires, the right assessors, and the right degree of cooperation, you can get a lot of valuable information really quite quickly. So to summarise, what kinds of architectural evaluation can we run? We can run scenario-based evaluation. Flexible and straightforward process. You can explain it to most people in a couple of minutes. You need some skill to actually do it, but then hopefully you've got facilitators who've got experience. So you can definitely run these. You can do it if you've got a system and you can talk about real tangible experience, or you can do it using the architectural design and how you think that will behave by using expert judgment. It's got a very strong stakeholder focus. It involves as many stakeholders as possible, gets them to drive the scenarios, and that's extremely valuable because you're focusing on the things that are important to stakeholders, why we do architecture. The problems with it are, firstly, it's quite costly in stakeholder time. Throughout my time in financial services, I used scenario-based evaluation on a number of occasions. I never managed to run an ATAM type exercise properly, as it says in the book. The reason was I could not get all those stakeholders in a single room for long enough, with enough focus and concentration to actually run the process. So I did all kinds of variants of it, euphemistically called lightweight or parallel or stakeholder-oriented ATAM. What it meant was I would often end up hypothesizing what the right scenarios were and starting to flesh them out, validating them with stakeholders rather than getting them to drive the process. And I would often deal with stakeholders either individually or in small groups because I just couldn't get them all together. So I lost the interaction and debate between them. I could bring other points of view into the conversation because I'd heard other stakeholders say it, but I could never really get the rich interaction that ATAM hopes for. The other thing is that you're very reliant on expert judgment. When you're evaluating scenarios, you need someone who's got a very good grasp of how the system works or is going to work, who can look at it and credibly say, this is what will happen. Now, actually, for older systems in large organizations that have been around for a long time, you may not have that person. So actually, that can be a bit of a problem with scenario-based techniques. How do you investigate the scenarios if you don't have the expert? The other problem with systems that haven't been built is it's a bit of a leap of faith. You're going through a thought experiment, and you hope when you implement the system, it will behave the same way as the thought experiment. Moving on to simulation. This is largely an objective process. It involves using a computer to simulate how the system will behave in certain situations. It's a very efficient process once you've got the simulator. Once you've got the simulator, you can run many, many scenarios through it at very low cost and get a lot of output very quickly. The problem is, where does the simulator come from? You typically need specific skills and tools to build these simulators, and these tools and skills are not widespread in an industrial context. Typically, building a comprehensive model to investigate one or more quality properties really thoroughly needs quite a sophisticated model, and it's very costly. As we said earlier, for an industrial architect, it's a tricky return on investment conversation with anyone. We're going to spend 6 or 8 weeks building a model that may or may not be all that valuable in predicting how our system is going to behave. That's not a very attractive proposition, partly because the validity of the results is very hard to validate. If you get a set of results from the simulator, how do you know that the real system will behave in the same way? And for non-trivial systems, and if you look in the research literature, most of the worked examples are trivial. For non-trivial systems, for example, hundreds of services, databases with thousands of database tables, it's really not clear whether the simulator will have much predictive power until you've used it quite a lot. That takes us to analytical methods, which are simpler than simulation-based methods, but inspired in the same way about abstracting some aspect of the system, in this case probably to a simple mathematical model. They tend to be simple and straightforward to build. If it's pretty straightforward mathematics, it's held in Excel that everybody knows and loves. It's pretty cost efficient to build. It doesn't take more than a couple of days and a couple of people typically. But these models tend to have quite limited applicability. I've used them certainly for performance and scalability, throughput calculations, those kind of things. For other qualities, it's hard to see how that kind of mathematics is going to give you much in the way of valuable evaluation. Again, it's quite difficult to validate the results, unless, again, you go back and test the real system. And if you've got the real system to test, maybe you should just test the real system. And analytical approaches, because you're trying to express it in a simple and elegant mathematical form, you may oversimplify the analysis. I've been guilty of this myself. I've built a number of these models over the years, and they've been of greater or lesser value, but a couple of times I've looked at the system, I've understood it quite well. There have been a couple of awkward details which were very hard to put into the mathematical model in Excel. They didn't really fit, so I just sort of factored them out, thinking they're probably not that significant. And what do you know? Actually, for some quite important scenarios, when we went back to look at the real system, those edge cases were actually key. I'd simplified them out simply because they were a bit awkward to put into my mathematical model. So that brings us really to empirical evaluation. That's all about the facts. What can we collect from the running operational system that can allow us to investigate its characteristics? It's fact-based by definition, that's a good thing. And because you tend to build a single big database of information, you can then perform lots of parallel evaluation for different kinds of system factors simultaneously. So that can be very efficient in terms of use of time. You can get a lot of information out of the facts quickly. The problems can be that it's quite difficult when you start with the data to link that to real insight. As we said earlier, it does help if you start off knowing the kind of things you'll want to ask, the kind of questions you want to ask, and then build the right measures into the system. But in reality, the questions you want to ask often emerge quite late in the day when the system's in operation, and by Murphy's law, you're always missing one bit of the puzzle. There's some data you're not collecting, which maybe you can change the system and start collecting it, but then you've got all this historical data which maybe you can't use, or you have to infer what that data was, making it less accurate. And actually for many operational systems, there's actually limited measurable data available. For a modern, highly observable system, you've probably got more than you can deal with. For many systems more than a few years old, you may have very little to start with, and you may be, fighting to add more measurement to the system, or you may be trying to derive a lot of information from, for example, historical log files, which is, a long and very tedious process, which can be quite error-prone. So finally, that brings us to survey-based evaluation, the most subjective, but also perhaps in some ways the most insightful, providing you're talking to the right people and that they have the right motivation to take part. Because survey-based evaluation allows wide participation. Everyone's got an opinion, you can ask everyone. It allows you to understand how people perceive the system. Perceptions and facts may be different, and even if you're doing empirical measurement, it can be very useful to know how the system is perceived. And you can cross-check answers to surveys that you get from different people. It's a fairly time-intensive approach, but it's reasonably efficient, especially compared to perhaps simulation, because we're not having to build a huge amount, but we are having to create a good, thoughtful, a structured questionnaire, and then take it to a lot of people, talk them through it, make sure they understand it, make sure that the answers we're getting are fair, valid, effective, accurate, and there's constant risk of bias and misrepresentation. And so it's very easy to miss part of the puzzle when you're doing purely survey-based evaluations. I've now been talking for about 30 minutes. I think there's probably about another 40 minutes to get to the end of the talk. So if you need a break, now's a good time to pause the video, get up, have a walk around, a cup of coffee and make yourself comfortable, and then come back and continue. So let's have a look at a couple of case studies of architectural evaluation in action. Now let's look at an example of scenario-based evaluation in practice. This is one that's a real industrial case study. It wasn't me, or it wasn't the company I was working for did it. It was a consulting company who made it available via some public deliverables, which was very good of them. It's very hard to get hold of real scenario-based evaluations. It's interesting because although it's a little bit old now, and the technology they talk about is quite old, it shows a real industrial evaluation driven by the needs of a particular situation rather than trying to illustrate the method, which many of the tutorials, of course, are very faithful to the method, but there's no real stakeholder. So actually, they're much more focused on the method than on the value that's being produced. And I think this case study is interesting for that reason. Just to recap scenario-based evaluation. So we want to identify the architectural characteristics of a system by considering the system's behaviour in response to particular conditions, that is, scenarios. It can be used with or without an implementation. If you don't have an implementation, you need an architectural description, and you're going to use either logical reasoning or experience or some kind of analysis or simulation to try and predict how the architecture will behave in certain scenarios. And if you've got a real system, you'll probably be using expert judgment, experience, and perhaps measurement of the real system to assess its behaviour. A lot of scenario-based methods exist in the research literature. To be frank, many of these have not been used widely in industry. But for a period, it did appear that the fashionable thing to do if you were a software architecture researcher was to invent another scenario-based evaluation technique. They've all got slightly different focus points, and they all emphasize different things about the process. They're all aiming to either address a limitation of a previous one or serve a particular kind of situation or set of constraints. The one that we're going to talk about is ATAM because it's the most widely used and it's the most mature, frankly, by quite a large margin. ATAM, the Architecture Trade-off Analysis Method, as it's snappily called, it's a second-generation scenario-based method from the SEI. Second generation because SAM was their original method and was very functionally based, and ATAM came later, building on the experience of using scenarios, but focusing it very firmly on quality attributes. It aims to provide an insight specifically into the trade-offs that have been made in the architecture, the risks that the architecture faces, and the implications of the architectural decisions that have been made so far. A strong characteristic of ATAM is that it's got a big focus on stakeholder involvement, and that's a great thing. It tries to gather a lot of stakeholders together, get them to work very collaboratively on identifying and validating the scenarios and really thinking about their joint needs. It's very well documented. There's a book on it. There are many white papers. There are a fair number of case studies, both in books, mainly from the SEI and the technical reports, and some other academic literature. You'll find occasional industrial case studies too, though as I alluded to earlier, they are far more difficult to come by. And it has been used in practice repeatedly, if nothing else because the SEI serves its customer base, who tend to be subcontractors to the US Department of Defense, and the DoD has asked for many ATAM assessments over the years, so it's been used in practice and refined repeatedly. It must be said, though, that full ATAM, running the whole method start to end, it's quite complex, and a full application can be quite costly, if nothing else because the review team tends to be a number of people, and there are quite a few stakeholders who all have to get together and spend time together. So it tends to be a process that is very suitable for a situation where the organisation that's running it is very committed to the process already, or frankly is being told to do it by a prime contractor such as the DoD. So let's recap a couple of ATAM key concepts. The scenario we've met already, it's a short story in effect. It explains that when the system encounters a stimulus in a particular environment, what response it should produce. So given a particular interaction with the system, and the system is running a particular state, what should the result be? When we're analysing scenarios, we are looking for risks, that's potentially problematic architectural decisions, or indeed situations where there is no architectural decision, and that is also creating a problem. Sensitivity points, that's decisions that have been made in the system that have an impact on quality properties. So, for example, a particular data structure may have an impact on the performance or the scalability of the system. That's a sensitivity point. And then a trade-off point, where we've had to look at the needs of more than one quality attribute and decide, frankly, which one is more important and trade off between them. Classic one might be between security and usability. We require high security, we've had to sacrifice some usability. That's a trade-off point. So ATAM is defining the process in terms of scenarios, and when we analyse scenarios, we look for risks, sensitivity points, and trade-off points. A key artifact of the ATAM process is the quality attribute tree, or QAT. The quality attribute tree is used to analyse the set of quality attributes that are required of the system. It's a fairly simple structure. It's a tree structure, as its name suggests. It starts off at the top with the quality attributes we're interested in. Then for each one, it tries to define one or more quality requirements. And then where it gets really interesting, it uses scenarios to illustrate those quality requirements. This is the antidote to the classic problem where quality requirements are so vague they're just truisms, such as the system must be performant. Well, give me a scenario that shows the system being performant. It's really good because it forces people into thinking about an example. And for each one, we define what the scenario is. Obviously, in this case, it's just the title of the scenario. We'd have to go away and work the scenario through. And for each one, we define the difficulty, how difficult we think this is going to be to achieve, low, medium, high, and the importance to the stakeholders, again, low, medium, high. The ATAM process sort of breaks into three phases, really. In the first one, we explain ATAM to the people involved. We can't assume that they know it well. Explain the business drivers. Why does this system exist? What is it trying to achieve? And then explain the architecture. What is the either proposed architecture or the real architecture of the system? How does it work? How does that meet the business drivers? We then identify the architectural approaches in use in the system. So that's the architectural mechanisms normally. How does the system achieve its quality properties? Once we understand the system, we then generate a QAT, a quality attribute tree, collaboratively, starting by listing the quality attributes important to us, defining the requirements for each, and then illustrating those with specific scenarios. And then we analyse the architectural approaches. And what that means is we step through the scenarios one by one, considering how does the system respond in that scenario to meet its required behaviour, which which of the architectural mechanisms, which of the architectural approaches is supporting that. And for each one, remember, we're thinking about the risks, the sensitivity points and the trade-off points that we're finding and recording those as we go. This is sort of the first phase of ATAM, and it involves the architect or architects, the review team, the sort of the specialists, if you like, and key stakeholders. There's a recognition in ATAM that dealing with all the stakeholders at once at the beginning is going to be overwhelming and probably counterproductive. So we start with people who are considered to be the key stakeholders, probably some of the most informed or those who have the most challenging quality attributes that they're interested in. And then it moves on to phase 2 with the full stakeholder group. We brainstorm and prioritise more scenarios. So of course more stakeholders arriving are starting to go, yes, but how about, and you've completely forgotten about my needs, I need the system to be able to do this. So they add more scenarios. We've already gone through the process of analysis, so hopefully we've got a good understanding of the system. We can very confidently start analysing those scenarios. And then there's a step 9, which is to present the results back. So phase 2 is done with the full stakeholder group. The way that I describe these is, what have you got? How does it work? Now let's prove that it works that way. And that's the overall ATAM process. As you can see, there's quite a bit to ATAM. Each stage has got a very good rationale. It all makes sense. It's all valuable, but it is a fairly involved process. In this example, we're going to look at the automation of a purchase-to-pay invoicing process. So that's how we go from buying something through to paying for it. In fact, we're not really going to get into the invoicing process very much. That's simply the sort of domain backdrop, so you understand some of the terms in use. It was an architectural design before a build by a consultancy called Inocom, and the evaluation was performed by a senior architect, Bart Veniclier of Inocom. They were consultants to the end-user organisation. This was released, presumably with the blessing of the end-user organisation, as an example of a practical use of ATAM rather than a training exercise. The background is that invoices can be posted, that is, recorded worldwide. They're all routed to one processing location. Presumably there is some centre of excellence somewhere in invoice processing. The processing group in that processing location, they label, as in they classify invoices, they scan them, and then they post them, that's the domain term, in other words they insert them into the SAP system for processing. So there's a process of posting an invoice into the overall system, that being transmitted somewhere, then human beings classifying, scanning, and then placing the invoices into the SAP system. You then, of course, before you pay anything, the people who actually control the money have to approve it. So there's review and approval by the budget holders, the SAP system, I think. And the stakeholders are not just the people using the system, but of course the procurement organisation is a stakeholder because they're overseeing the process and want it to be well controlled and efficient and visible and so on. And the legal and the finance teams, well, the legal team want to be very clear that everything we're doing is legal and the right contracts are in place and so on. And the finance team, of course, want to have oversight of the cash flows to ensure that they're controlled adequately. The constraints that were explained to the architect performing the evaluation are that they wanted fast time to market. Well, of course, have you ever met anyone who said they wanted slow time to market? People always say that. And they wanted a good end user experience. It needed to be easy to use and quick, which, given some of the other constraints, is actually quite complicated because although they wanted a good end user experience, they must use the corporate SAP and Documentum standard software. Well, neither of those software packages, even when this was done a few years ago, have a reputation for being particularly easy to use or particularly quick. And in fact, not necessarily supporting fast time to market either. And of course, they wanted it minimal cost. Again, it's the classic project. They'd like it at zero cost in 0 time, please. It also must run in the existing infrastructure environment. You'll see this reflected in an architectural view in just a moment. But what this means is it's got to run on the corporate platform. The people implementing it are not free to go and introduce new operating systems, new hardware platforms, new kinds of storage and so on. They've got to use what's in the corporation. When the assessor arrived, he found that there wasn't really an architectural description, so he had to create one. So rather than create a really kind of I suppose, what you'd call a really sound, reusable, highly insightful architectural description. He, of course, had to work very quickly because he was inside the review process, and this was blocking the process. So he created a functional view that's extremely focused on the needs of the review. So it's minimal. It only shows the components, the interactions, and the interfaces which are relevant to the review. And it's a bit odd in many ways. It shows a number of different concerns on the same diagram. But of course, why has he done that? He's done that so he can explain the salient aspects of the system to the people who are involved in the review as quickly as he can. So he doesn't have to explain to non-technical stakeholders or people who've never heard of architectural reviews why he has got, for example, a functional view, a data view, and a deployment view, or an operational view, and a deployment view, and an information view, or whatever he might have done in a sort of idealised world. I'm quite sure the reviewer knew how to do that, but in this case, he created an artifact specifically for the review. And you can see it's reasonably straightforward to understand. Captiva is a scanning system. It's used to scan invoices and also archive them off, presumably for compliance purposes. It sends things via a queuing system off to Documentum. That's a document processing and storage system. SAP, good old ERP system sitting in the bottom left-hand corner. SAP and Documentum aren't connected, so they're creating what they're calling an e-connector task. Interestingly here, Windows 2000 suddenly appears. This is where I say that's a deployment view thing, surely, but he's just, to keep it all together, he said, look, Windows 2000, it's a service interface into the eConnector. The eConnector is a Windows 2000 service. I am using your corporate infrastructure platform. He's sort of making the point. Then there is a separate user interface in front of Documentum and SAP. So there's a document viewer and a verification and approval tool. This, I think, goes back to being easy and quick for people to use. They've realised that getting them to log into Documentum, logging into SAP and using those workflows isn't going to work terribly well. So again, slightly oddly, he showed that they are browser interfaces by putting the browser on the diagram. But we can get the idea that the document viewer and verification approval tool are browser-based applications which connect to Documentum and SAP in order to provide better user interfaces. And finally, there's a post tool to allow posting of invoices. So that's a fairly unconventional functional view, it has to be said, but you can absolutely see why this assessor created it to explain what he needed to explain quickly to this particular audience. There is a bigger quality attribute tree in the interest of putting it on a slide. This is an example of a bit of it. For performance, he didn't really go into requirements. He really just kind of decomposed what he meant by each broad quality area. So for performance, he said there are some latency requirements and some throughput requirements. For latency, there was more than this, to be fair to him. An example is opening an e-document, as it's called. That's obviously a bit of local domain jargon from Documentum. It takes less than 10 seconds from any site, and that's going to be difficult, but it's also very important. Similarly for throughput, if people are opening documents at 2 documents a second, then the average response time has got to be less than 3 documents from any site. Availability, a site disconnect due to a network failure has to be reconnected at a certain time. Failure of a particular server has no effect on availability. If the eConnector loses its SAP connectivity, then this mustn't result in less than 99.25% availability. I'll refer you to the slide for the full text. Sorry, I've just realised that the video partly blocks it, but you'll see it again in a moment. Look at how they then developed these scenarios into the architectural analysis they needed. Looking at the first one, which is that an invoice poster needs an e-document for data entry into SAP. So this is the performance and latency one. This is the document request into Documentum, I think from the document viewer, and it has to be available in less than 10 seconds. And so there were a couple of architectural decisions the reviewer uncovered that supported this particular scenario and gave him confidence it could be met. So e-documents are scanned at 200 dpi in colour, which is actually pretty low resolution, right? The sensitivity point was the size of the document is sensitive to the quality of the scan. So therefore, we have a sensitivity point between the resolution we're going to scan the documents out and the speed we can pull them back out of Documentum. And it's a usability versus performance thing. Those 200 dpi documents may not be as usable as, say, 600 dpi documents, but they support the performance goal. and the risk is the document retrieval will actually go over 10 seconds. Then the e-documents are not going to be cached in SAP. Every document must be cached from Documentum. So having made that decision, the sensitivity is we've potentially again got a performance problem because every document's going to come out of Documentum. And the reason for this was development cost. They worked out it was actually SAP's a difficult system to work in and configure. And as it happened, it didn't really support this. So that was going to be a fairly big job. That's development cost versus performance. And again, the risk is if they get this wrong, the document retrieval will take far too long. The second example scenario, the e-connector, that was the bit that, if you remember, between Documentum and SAP, their custom software, that loses connection with SAP. This must be something that they were aware of because they've picked this out specifically, that perhaps they've had problems with SAP APIs before, that they get shut down or that there's a problem with them. So this is overall availability. And it could be caused by a temporary network fault. Perhaps they know something we don't, looking on afterwards about the network connection to SAP. And the response must be that the system maintains an overall availability of 99.25%. I have no idea where that number came from. And in this case study, even the fuller version, there was no hint where the number came from. So those fascinating things that if you weren't there at the time, you've sort of lost that context, and that because they didn't record that very clearly. I imagine if they went back now and looked at it again a few years later, they'd go, yeah, why did we say 99.25? But we'll take it as a requirement that was validated by a stakeholder. And so for this decision, they're going to run the Documentum server clustered on 2 nodes. The sensitivity of this is that they are still vulnerable to a common mode failure. So if there's the same problem on 2 servers, they've lost Documentum anyway. They didn't see any particular trade-offs with this, and they believe that they've identified a non-risk is that common mode failures have very low probability in their experience. The other decision is that the integration between SAP and Documentum is going to be consistent data but not transactional. In fact, I think today what we probably call this is it will be eventually consistent. The sensitivity, apparently, is that human users will have to spot the inconsistency so it can be resolved. And that means that resolution is likely to be quite long, and the inconsistency may be long-lived. And they've identified that as an architectural risk. And so on the process went. Not wanting to go through all the scenarios. Then moving on, as they went through the other scenarios, there were a number of other architectural risks that they spotted. The first one was another performance latency problem. They spotted that a lot of small SQL queries were being used for some of the interactions with data stores. They, from experience, knew that this was going to cause high latency. A problem we still see today, actually. Modifiability, when they thought about how this system was going to be changed over time, the applications were monolithic. They knew from experience they were quite difficult applications to change. That was an obvious risk. The organisation of components, this isn't obvious from the functional view, but obviously it was a result of expert judgment looking at the proposal for how the data structures work, but that the organisation of components was going to cause rippling change. So for example, if the invoice capture data structures changed, the architectural assessor noticed that there was going to be change needed right through the system in order to support that change, which is difficult to implement. And finally, there was no test infrastructure for safe refactoring, not in itself part of the architectural design, but a really important environmental problem, which means that people will probably be very cautious about doing refactoring and might not want to keep the design optimal because actually they're quite worried about refactoring something because they're having to effectively test it in production. And then they also noticed a number of security problems, that apparently there was poor input validation, so therefore the system could be subject to injection attacks, it could be subject to fuzzing type attacks, it could be subject to misuse by stuffing parameters and so on. And there was also apparently fragmented user management. If you think back to the functional view, there's a number of systems there that may well have their own user identification and access control. I mean, SAP's probably got it, Documentum might have it, Windows 2000 definitely has it, and the web app actually might have its own as well, or it might be using the Active Directory. We can't tell actually from the artifacts that were created, but clearly as they worked through the scenarios, they realised they had a problem with fragmented user management. So that's an example of a real architecture review for something that's not, if you like, a pure piece of software development. It's a typical kind of enterprise software implementation problem, and an ATAM-like process, a scenario-based process based on ATAM, has been used to evaluate it and produce some really quite important findings, which the stakeholders need to be aware of before they go ahead and commit to build this thing, that there are some trade-offs that they're getting themselves into. Perhaps now's the time to think about revisiting some of those decisions. As I say, you can tell as we went through it, it's by no means an academically perfect example. We wouldn't probably use this for training, as in training people the correct way to do ATAM. It's obviously the result of somebody who knew ATAM, was put into a real context, and applied the right bits of ATAM to get value, to get insight for the stakeholders who were concerned. And that, to stress once again from earlier in this talk, it is important to bear the context in mind to make sure that we're creating the most valuable, insightful outputs we can for the time and effort that we're expending on a particular system. Moving on to empirical evaluation. You will recall that empirical evaluation is about measuring the system, measuring some aspect of the system directly. This uses an approach, a very simple approach, which I came up with called TARA, which is the Tiny Architectural Review approach. It's an empirical evaluation because it measures the system both in its implementation and in its operation, and that's what it uses as the core of the evaluation process. This case study came from the asset management industry. I performed it. TARA actually came out of this exercise. So TARA, if you like, the TARA model is a slightly tidied up version of what we really did several times when we were looking at real systems. The driver for the review was that an existing system was perceived as deficient. So a request was made to assess its quality. The process needed to be fairly quick with limited stakeholder involvement. And it was just one architecture assessor, happened to be me, working with the development team, which is obviously slightly uncomfortable because they realise their system is being, reviewed for some reason that is not entirely clear. The first problem, of course, was that the senior stakeholder, who was a VP of software engineering or something like that, wanted to assess the system's quality without being very clear what quality meant. And that was one of the first problems in it, which we'll see in a few minutes. It became clear to me ATAM was not going to be accepted. There was no organisational history of structured organised architectural assessment. There was a desire to keep it simple and lightweight. Those were the terms that kept being repeated to me. It's also realistically, when I looked around at the people I needed to talk to, the chances of getting them all in a room for this particular exercise for any length of time was approximately zero. So a much simpler approach was required, and I felt an empirical approach required using implementation artefacts was going to be much more successful than starting it with scenarios. So this very simple approach is that you gather the context and requirements of the system as best you can. You create functional and deployment views so that you understand what you're looking at. And then the empirical part is you do code analysis. You understand the system by analysing its code and mapping that to the views. You do a requirements assessment, as in from this code and anything else we can find, any empirical stuff we can find. Are our architectural requirements likely to be met or not? We then move into a reporting part, and it's quite important to note that the assessment and the reporting are different. One of the things about TARA that's important is that it was specifically created to answer a stakeholder's request for information, not to perform any sort of generalised assessment of a system. And that's another thing that makes it a bit different to ATAM. Rather than starting with a kind of very broad view, it starts with, what is your question? I will now go and get you an answer to that question, which is very, very often the context for an architectural review. So you then identify and report your findings. You create very specific conclusions for the sponsor, the person who's asked this to be done, and then you deliver findings and recommendations, both at the sponsor level, which obviously are summary and are very focused on their questions, but also broader, in a friendly and kind way, to the team as to how they can make improvements that you've observed would be important to make. As I mentioned, one of the things about TARA, one of the reasons I created it, was it's for the kind of review where you've normally got a pretty senior stakeholder who's got some very specific questions they need answered pretty quickly, often about an existing system. Nearly always there's a code base that we're working with. In this, so the first place you have to start is what question are they actually asking? And in this case, as you will have seen on previous slides, they were rather unhelpfully asking, is this system of good quality? And so that was my starting point. And of course, to an architectural evaluator, that's a pretty meaningless statement, or a pretty meaningless question. I mean, what does quality mean? So I sat down with that key stakeholder. Luckily, he was someone I got on with well. And what do you mean by quality? That's not a useful statement. So once we talked about it quite a lot, and we broke it down to about 4 things that he was really worried about. Are the financial modelling fundamentals sound? I don't know too much about these developers. A lot of them have got a very mathematical background. I don't know much about their software development. I'm afraid that it's just been hacked together, and actually it doesn't even run models properly. And actually they've probably put lots of hard coding in the models, so it's probably really hard to change the models when we need to make them flexible. So can we define the models we need? Can we change them easily? Can we manage lots and lots of executions of the models? Because that's actually what we need to do. That's what we mean by financial modelling, to build a model and then run it lots of times. Can we track the inputs and the outputs? Is it usable by the fund managers? Because we've built lots of systems in the past which was big heaps of Perl and Python scripts. And honestly, nobody quite knew when things had been run, and they were hard to use because you couldn't run experiments with them. You had to change the code, and the fund managers hated doing that because they always broke it and. Okay, so what you mean by usability by the fund managers is, can they run lots of variations to a particular model to explore a theory? Yes, that's an important point. And secondly, when they're running these variations, can we track them, track what they've done, and capture the outputs reliably? So that if we need to go back and say, why did we end up buying this security? And the fund manager goes, well, I ran my model and I changed these weights and it looked like a really good bet. They went, let's just go back and look at the model. I mean, today they just couldn't do that. What happened was they'd run it on their desktop. Again, it was these big scripts, which they were never quite sure what version they were running. The output was a CSV, which they pushed into Excel, took a look at it and went, yeah, that looks like a great option. Let's go and buy it. Or not buy it directly, but, let's go and now change our trading model. So can we track what they've done in their experiments and capture the output so we can go back and actually ask some questions? Is it going to be fast enough for our models? One of the problems with the scripts is that for some kinds of model, it just takes hours and hours to run. This is running on server-side, enterprise-scale hardware. It should be a lot faster, but is it? Again, these guys are statisticians in some cases. I'm not sure they know about writing performance software. And our models are getting bigger with many more dimensions. Is it really going to be fast enough for us to be useful and valuable over the long term? Okay, so fast enough. That means fast enough today, fast enough tomorrow with more aspects to the model. Got it. And then will it scale? Scale. Again, what do you mean by scale? There are many dimensions. Turns out there were 2 things really. One was this bigger models thing. We're going to have models with many more dimensions, possibly more accuracy, fidelity in the models, which makes them much more computationally intensive. So more model computation. Is that possible to do in this system? Because in the scripts, it's definitely not. They keep hitting brick walls there. And secondly, a lot more fund managers and regions want to use it. And having invested in the system, we really want to know, should we keep investing? Could we use it in other places? Because if we could, that's a great return on investment, because they've all got their own heaps of scripts and they're probably going to build their own system if this isn't rolled out to them. So is it suitable for being rolled out to many more fund managers, so lots more people accessing the system, much more concurrent use? And if we want to use it in other regions, so this was mainly being done in London for the European region, if Tokyo want to use it, could we use it? That sort of scalability, which is, really probably functional variation as much as technical scalability. So we pulled it down to those were the questions that we needed to answer in this review, and that really helped us and gave us some focus. So, delving in a little further, we then continued to create a context diagram for the system, partly based on what the team had, but the team didn't have a terribly structured context diagram, so we created one, which wasn't very difficult. As I hinted in the questions, this is a calculation system. It takes a number of input data sources. It allows portfolio managers to define a quantitative model to allow them to explore various kind of fund management fundamentals based on those input sources. The input sources typically known as signals. That's things like changes in price, changes in daily volume of stocks being traded, and so on. There's an existing analysis system. They get some of their data from there, which is some values which have already been calculated out of its models, some other signals which don't come from the strategic sources, and things called T-costs, transaction costs. Transaction costs are obviously important because if when you're trying to calculate, is it worth doing a transaction for a particular period? If the profit is X and the trading cost is 1.2 times X, then your trading cost is going to be higher than your profit. You don't make the trade. So transaction costs are important too. So what this system does is that it allows people to define quantitative models in the system using a specific client, quite a fairly sophisticated client, visual client actually. It takes in signal data, as it's called, sort of raw signal data from various sources. It takes in some more information from a legacy system that hasn't yet been replaced, and it then runs the statistical models, probably repeatedly actually, for lots of different variants and input parameter values, and out come the calculated values, the results of the model. The signals themselves are passed on as well. That's the signals are cut down to the set that support the model, so it's not a complete signal set. And the transaction costs relevant to the model are also pulled out, put into effectively a data set, and passed to a portfolio management system. And it's the portfolio management system that manages the whole process of deciding what to buy and sell, keeping track of what has been bought and sold, keeping profit and loss, and interacting with a trading system to actually perform trade execution to maintain the portfolio. It had some quite decent requirements actually, and this is a snapshot. They weren't captured very formally, but actually when you talk to the stakeholders, people were pretty clear what they were, which was great. It was about creating a quantitative model that creates those calculated values to be defined and then run on demand whenever. The model clearly defined input data sources, calculation, status, as in are we calculated or not, and output data, and it produced things called quantity and cost values, which are the output which go into portfolio management. There was also the ability to override particular parts of the model for particular executions, and this is quite an important part of quantitative portfolio management. There's quite a lot of experimentation by overriding particular values, rerunning your models, seeing what would happen to your portfolio, and then going back and deciding whether or not to change your model. Then performance, there were some quite specific. This is fundamentally a batch-based system, but some quite specific performance requirements. The portfolio managers knew what reasonable was. And also scalability was that they knew what their user base was going to be, and they had a good idea as to how big a model they were going to have to handle. So that wasn't bad. That was a better set of requirements than I was expecting, frankly. Although I had to do some of the capture, and obviously I've summarised them and anonymised them here so that you can't trace them straight back to a real system, they really weren't bad. I then created a functional view because this system was in operation. There were questions about what its future should be, and so I created a functional view. And actually, to be fair to the team, I was quite pleasantly surprised what I found. That, as you can see, is a pretty structured model. That's not a completely theoretical, idealised, tidied up view of the system. That was pretty well the system structure. Yes, there were some complications in the code structure, which I'll show you in a moment, but actually that was largely, that was a combination of expert input and then reverse engineered from the code. So it was synced with the code all the time. You'd normally also add a deployment view, as in how is this thing deployed? Where is it deployed to? What are its critical runtime resources? How does it get operated in production? All that sort of thing. I haven't shown that here, but we did actually do one of those too. Then we moved on to the empirical part, which was static analysis of the system. How big is it in terms of code structures? How big is the implementation versus the testing? How is it organised? What are the structural metrics? And we were using a tool called Structure 101 and its XS metric, which is about excessive complexity, structural complexity, and in particular they spot things that they called code tangles. That's areas where they cannot create a tree, in effect, that you've ended up with a graph which is self-referential, and that's a tangle. And they identify percentages of code that tangle, where it is, what it's connected to, and so on. The diagram at the top is an example, suitably small, so you can't get too close to it. That's one of many, many diagrams we produced to visualise the information that Structure 101 and some informal, scripting tools I think we created in Perl it was a few years ago. We'd use Python today, it would be far cooler. But we wrote some Perl tools to also analyse code, use reusable Perl modules to extract metrics from code and then process the outputs. And then that led us to some specific findings and implementations, is that the model implementation was very well done. The fact that it was all data rather than code means that it was very evolvable, etc., etc. Internal dependencies, it's not a bad start. At the macro level, it's all quite good. When you get into the detail, actually, there's some bits of it are a bit of a mess, and now's the time to fix it. It's perfectly fixable, but you need to fix it now. Recommendation, nobody knows how to run this system apart from the dev team. That's not scalable. It's going to go off to other regions. It's going to be a disaster. Document it. And then also about, they hadn't really thought about variability points. So they, without really thinking about it, were going to have to build a product line, a simple product line, but they were going to have 3 or 4 of these instances of the system, all which worked a bit differently. In other words, a small product line. And they really hadn't thought about that at all. So again, that was an insight we could bring to bear. So in terms of the original stakeholders' request, quality, we refined that to what quality might mean, which is the qualitative aspect of the system fit for purpose? Is the system maintainable? Can the system be used in different regions? Can the system be operated safely? And we produced very specific findings and recommendations for those to answer the sponsors', as it turns out, implicit question. Now let's look at the strengths and weaknesses of Tara as an evaluation method. Starting with the strengths, its key one really is simplicity. It's easy to understand. People can quickly understand what they're going to get. You can show people the process and they immediately understand what's going to happen in each stage. And actually that's pretty important for industrial acceptance. People are quite mistrustful of complicated and, as they see it, overly sophisticated processes that they don't really understand. It's also extremely rooted in the implementation structures. That's important for 2 reasons. One, it's the empiricism. It's the fact that it is rooted in facts, even if, of course, there is some subjective interpretation of those facts. And also the fact that, from a practitioner's perspective, the code is the reality of the system. They really like it when you base an architectural evaluation on the tangible code that they can also see and understand. And you can have a discussion about what the code means for the architectural qualities, rather than a much more abstract discussion about, say, architectural mechanisms. It brings structure to an ad hoc situation. In reality, when a lot of these reviews are performed in industry, somebody who doesn't really, frankly, know anything about architectural evaluation is asked to evaluate an architecture. They just start, they do what seems sensible, they stop, they write it up. It's a very ad hoc approach. Tara brings a very simple, approachable, amenable structure to a fairly ad hoc situation. It's valuable for that. It's quick and it's efficient to run. I did this one in probably a couple of hours a day, and it probably took a little bit over a week. I had a little bit of help from one of the architects in my team. And of course, I had input, and I spent time with the stakeholders around the system, both technical and non-technical. But really, compared to, say, an ATAM review of developing scenarios, going through the analysis very rigorously, involving then a big stakeholder group and doing a lot of formal reporting, it was quick, it produced results quickly, and it got the stakeholder specific answers to specific questions that he needed. And if they'd been much later, they would probably have been much less valuable. So, although, of course, there's a trade-off about its depth, the speed and efficiency are important to its real application. It also, by design, produces simple, concise and usable outputs, very directed at the questions that were asked at the start of the review, and that, again, is important to acceptance. People find it's accessible, they believe the output, they get the answers they need quickly. It, of course, has weaknesses. It's really rather simple, and it relies definitely on the subjectivity of the reviewer. There are ad hoc elements to the process. It's not as structured as ATAM. There's not as much guidance. I rely more on judgment. There's also a lack of mandatory trade-off analysis. In fact, I think it does say in the paper, trade-off analysis is encouraged as you go through to think about the trade-offs that have been made, but I actually haven't got a step. Perhaps there should be a step to explicitly say, stop here and think about the trade-offs. It's something that I'm relying on the experience of the architect to do. The fact its primary input are the implementation structures, I've just said, is a strength. It's also a weakness, of course, because actually a lot of the architecture isn't in the implementation structures. There are no architectural structures in most code. Architecture is represented in code typically as a series of naming conventions and often not much more. So as you saw, we created a functional view. We also didn't show it, but created a deployment view. So we create those from the code. And although the code roots us in. The fact that we are so driven by the code is also a bit of a limitation in that we probably don't give as much thought to more sophisticated architectural structures as perhaps we should. And it's a relatively shallow assessment. In a sense, you get what you pay for. It's quick, it's lean, it's efficient, you get answers to specific questions. That means that you just don't get the same depth of review as you would with a method such as ATAM. So while I created Tara, obviously I think it's useful, I've used it on quite a number of occasions, you have to bear in mind that it is a simple, relatively shallow approach for answering specific questions in a specific situation. So, just moving on now to what architectural evaluation is like in my experience in practice. Common problems with evaluations, which you should be aware of, is that evaluations are often performed too late to be as useful as they could have been, or they're not performed at all, which is the ultimate problem with evaluation, is that it just doesn't happen. People, just blindly continue on, hoping that everything will be fine, not really thinking about how early they could validate things. Often reviews have unclear objectives. I mentioned this with the Tara example. It's all very well saying, what's the quality of the system like? But unless you clearly define what quality is and why you want to know, then actually it's very hard to do the review. And so that's why the beginning of the Tara process was very much talking to that key stakeholder, who luckily I had a good personal relationship with, to try and drill into what he actually meant by that. It's very often an unstructured opinion-based process, and the people who shout loudest get their views into the report. There's often a lack of validation of those opinions, and that's really the point. I think expressing an opinion is fine. I think capturing opinions and contrasting them is also fine. Perception is important, but when you don't validate the opinions, then I think they're just not worth very much, because you don't know if you can rely on them or not. And you often get personalities rather than data driving the process. So that's often the context you're working in industrial evaluation context, with you can see a lot of socioeconomic factors rather than pure technical factors. But a major benefit of running any kind of architectural evaluation in industry is getting people to talk to each other. You'd be surprised how little the different stakeholders talk to each other. Just getting them round this kind of shared question of, is this any good, can actually be very beneficial in itself. Dangers I observe with evaluation methods are that the structured methods look logical, sophisticated and structured. After all, there's a peer-reviewed publication which describes them. There's nothing blows most industrialists away like a peer-reviewed publication, which, as someone who's written a few peer-reviewed publications and reviews a lot, I quickly disagree with when they produce a peer-reviewed publication and say it must be true. I say, let me explain about peer-reviewed publications. You all know the dangers of relying purely on peer review. We need to go and test stuff as well. And so a lot of these methods are not actually very well validated. They've been perhaps tried on a couple of small things. And in reality, when you look at them, a lot of the scenario methods are not much more than structured common sense. I want to know how my system's going to behave. Well, why don't I think about what comes in, what it does, and what comes out? I don't wish to belittle a useful technique, but actually when you get to the core of it, there's not a lot there. Scenario methods, ATAM in particular, has wrapped a lot of sophistication around it, but the basic core of it is very simple. Analytical methods, very sophisticated in many cases, bit disconnected from reality. You don't really know what their predictive power is unless you already understand the system in enough detail. You probably don't need them. And empirical methods, they tend to be measuring things very precisely, but as we said earlier, going from the data, from a measurement to insight, is often very difficult. Key thing I would ask you to take away is that every review situation is different, with both technical, social, political and economic factors which bear on the architectural review being performed and make it different and cause the prioritisation of different activities and the value of different activities to change. And most architectural evaluation today, despite the methods, whatever we are asserting about the methods, it's highly dependent on the skill and knowledge of the participants. The practical advice I can give you from Indava's experience is get the scope right. Too narrow a scope, no one cares. Too wide a scope, and you drown, and you can't produce the focused outputs that the stakeholders need. Get the focus right. Even once you've got the scope, do you know what question they're actually asking? If you don't, or you don't understand it, go back and talk to them enough to really understand the question and why they're asking that question. Get the politics right. we get this wrong as often as most engineering consultancies, but we are very aware of it, having been bitten by it many times. Who cares that this is happening, and why do they care? Are they positive about it? Are they negative about it? Are they threatened by it? Do they see it as an opportunity? And do they see it as an opportunity in a positive way, or simply an opportunity for themselves? I mean, who's in the mix? What do they know? What are their goals? Therefore, how do you need to treat them? Constantly focus on value. We find most of our assessment exercises are about 6 weeks long, 2 weeks discovery, 4 weeks of exercise. We find that we have to adapt what we're looking at all the way through that, because we learn more and more, we talk more and more to the client, and we find actually what we were planning to do is of much less value in this other area we could go and look at instead. So always focus on, are we producing something that's valuable to the stakeholders? Is it producing valuable knowledge? And if not, adapt. Don't worry about the method or the plan or the fact that we've promised a report with the following headings. Go and talk to the people we promised it to and say, here's what we're actually going to do, here's why. Identify your information sources early. It can take a long time to get information, particularly in large companies. And going back to the politics, sometimes some people are very motivated to make it difficult. Identify them clearly. Make sure you understand what's in them, how reliable they are, and how to get them. Structure and undertake interviews carefully. It sounds sort of obvious. I've got some questions. I'm going to talk to someone. How hard can it be? We've actually found that especially new, more junior architects, less experienced people, really find it very difficult to interview people effectively. You've got to be positive, constructive, non-confrontational, while still holding them to account, validating what they're telling you, recording it accurately, making sure that they're committing to the process and being open and transparent. We often find that 2 interviewers are actually required. One who mainly focuses on structure, process and recording, and the other one who's really asking the questions, assessing the information, thinking about what's going on in the dynamics. Validate everything you find or you're told. If you find an old document, go and find out if it's still valid. If you find a new document, find out if the content is actually valid. We've made that mistake a number of times of being handed documentation, assuming it was correct, and sometime down the line a senior engineer going, oh no, they didn't give you the theory of operation document, did they? Oh, that's just theoretical nonsense. I mean, some architect wrote that down. It has no relation to how the system works. You go, oh no, we spent 2 weeks working with it. And same when people tell you things. We never get any outages at night. We never get an outage at month end. We've never had a month end run long. Okay, you got any data to show that? Or if you're not talking to somebody from operations, don't say anything, just record those as facts, put question marks by them, go and talk to operations. If it's run long at the end of the month and it's caused a problem, ops will know. They'll probably have an incident log that told you why it happened. And don't just be an architect. Don't just look at software structures if that's your thing. If you're an enterprise architect, don't just look at application structures. Got to think about application management. What does it like to run? DevOps. How's their continuous delivery process? Do they test it effectively? What's the security like? All of these things have a potential impact on the quality properties of the system. And so one of the things we need to bear in mind is that approaches like ATAM have been around for quite a few years, and things have changed in the industry since they came out. Agility came along, so we started delivering software in much smaller increments, adapting what we were doing as we learned more. Cloud computing came along, meaning that we could change our infrastructure by changing a few lines of code and redeploying it. So suddenly infrastructure became software, much more adaptable. Microservices came along, the reason being we wanted to put change into production far quicker, and we realized it was probably less risky to change a couple of small things than to change one huge monolithic thing. And finally, DevOps came along because we did all this without really involving ops very much, and that didn't end well. So now we're working in cross-functional teams where we're getting the ops colleagues involved right through the software lifecycle and dev colleagues involved right into the operational part of the lifecycle. And all this means we are producing much more fluid and evolving architectures than we did. That's quite important because constant evolution means there's less certainty early in the lifecycle. Less decided early in the life cycle means there's less value in a very thorough, big upfront architectural evaluation. So architectural evaluation needs to become more dynamic, more continuous, working through the life cycle if it's going to remain relevant in the age of agility and DevOps. I think that's something to bear in mind when so much research is still dominated by thinking based on ATAM and SAM. And I'd urge you to think about that in your research, whether you're researching evaluation or not. So quickly, the conclusions. Architectural evaluation can be valuable. I know I've criticised it a lot, but actually it's immensely beneficial. If nothing else, as I said, get the people talking. But there are many benefits, and some of them are quite unexpected. You can discover something during evaluation, put it in your findings, and suddenly someone in the organisation realises something really important as a result. And as an industry, we should do a lot more of it a lot earlier. We tend to do it in crises, we tend to do it in mergers and acquisitions, and that's way, way too late. It should be, as I say, especially with continuously evolving systems, we should be doing it continually. Scenarios are a very proven approach to structure the process, and they are of definite value. In fact, they're simple, they're straightforward, they can explain them to all the stakeholders, and they really help to structure things in a very logical, methodical way. Empirical data is extremely valuable, and you should always hunt it out when you're doing any sort of architectural evaluation. Surveys are pretty common, and as I said, they are valuable and they're popular for good reasons. They're pretty efficient. They allow you to gather a lot of information quickly. They allow you to compare different viewpoints. They allow you to compare data versus perception. That's all valuable, but they have a lot of dangers. You get a lot of perceptions back, and you need to spend a lot of time validating what you're told and comparing inputs. You also tend to only get back answers for questions you've asked. If you've missed an important question, they may not tell you voluntarily. Simulation and analysis are probably the classical research approaches to evaluating architectural properties. They need used with care because they're very powerful, sophisticated techniques, but if they're not tightly linked to reality, they're actually not of all that much use because their predictive power is very weak and they can be quite expensive to perform. Finally, don't rely on the method, whatever method you're using, whether it's a method you created this morning, please don't, or a lightweight version of ATAM, or you did a full ATAM assessment, or you're working with a simulation tool. Remember, it's the evaluators actually make the difference, not the tools. The tool or the method is there to support the evaluator's judgment. And so developing good judgment is what's key. And finally, be aware of the pitfalls. We talked about a few of them. Remember, a lot of those pitfalls are to do with the people. And that's the thing always to come back to. Architecture evaluation happens in a context, and a big part of that context are the people involved. Thank you for your attention. I hope you found that valuable, and I hope that we can discuss more during the event.